Hi, sorry, I just now I didn't hear you clearly. Yes, unfortunately, I'm in the car, but yeah, it's okay.
Yeah, I saw you were in a car. Where are you? You're always driving somewhere, I think.
Yeah, he is true.
No, yeah, it's a little bit errands about some design coffee shop, but it's okay.
Are you living in a car or something?
Sorry about this.
No, it's okay.
No. Yeah.
A small question. Did any of you join the Theos Symposium on the machines, or was over? I don't remember the full title. On Friday?
Live machines and stuff.
Yeah. No.
I didn't manage to. I think it would be interesting. I'm pretty sure it's recorded.
Yeah, I didn't manage to, and I would like the recording. But I guess that we will upload that at the AA.
I think the AA website would have that.
Okay. But they haven't uploaded that yet.
But it was a very long session, no? Like 5 hours or something.
Indeed. Okay, we will quickly go through our work too. As we said the previous time, we had these 4 main chapters and the computational research. So I guess that we don't need to focus on that. No. Phenomena, behavior, technology, and populations on water. And then we start with the different strategies and the phase changing thing, and how we simulate as an abstraction. Then we move forward to the flocking abstraction. We set our rule set based on separation, attraction, alignment, speed, and observation radius. We set a gradient of values for each phase. So, we start. Each phase is a gradient. It's not something solid. It's not something defined from like the maximum temperature to the minimum. So after we set, we define our phases. We're trying to relate these variables to temperature. So we find the values that we relate to the phase change, when phase change happens. And the temperature is introduced as a variable that we tweak only that, and we get phase changing. I guess that this is a new work that we haven't seen. Yeah. For example, here maybe we can see better the gradient of the phase change from the liquid to gas, from gas to liquid, and to ice. This doesn't play. Anyway, then we try to trigger different behaviors across the phase changing by changing in a different pace the temperature value. So here, for example, we try to, trying to get an unexpected result, because otherwise we got this monotonous result of phase changing. Okay, so here we try to do the instant freezing. So, and we get this result of ice, which is less dense and more, I don't know, somehow. We could say that it resembles a snowflake. And here we go from this to this separate drop formation for a liquid. And then we try to control our liquid with a target as an influencer, thinking about a bending behavior, for example, here, how we could resemble the bending behavior. I'm sorry, something. Okay, Or no, something. Yeah, so disruptor. And then by controlling a cloud of gas, which I think is interesting here, these two examples, because
but beyond the computation, the computation control, how that happens in real life?
Yeah, these are the questions that we have to discuss now. I just quickly saw the latest development in terms of computation, that we also introduced heat, and we tried to create patterns by changing heat across the population, by changing temperature, let's say.
A lot of work in a week, huh?
Yeah. Yuji did good work with coding. She did this last part with heat like few hours before the presentation.
Yuji, always having something hidden under your sleeve. That's the ace.
Like, what? I think at 12, like the previous night.
Yeah. I mean, that's a good thing with computation and scripting. Sometimes once you set it up, you produce more than people think you can. Actually, I do that in the office a lot. I try to do everything with Grasshopper. So when I have to do a tricky task, I set it up there and I tell them, look, it's gonna take like 3-4 days. I know it's gonna take 3 hours, but you play with the sliders, you get some output, and everybody says, "Oh, how do you make it?" Hard modeling. Sorry.
Yeah. So we try to see how patterns could emerge from this by introducing areas of different temperature in the same population. Could be something interesting here, and then we said how we can move on to the environmental scale, but we have no such example to the larger scale. So yeah, briefly.
Like even that, going to the 3D scale, I think it would be quite interesting. I don't know if that's 3D, but you saw 2D. But
yeah, we did also the 3D for this part, but I think that the result, the outcome was more maybe in the 2D grid. Here is the 3D grid.
Yeah, no, I think there's more clarity in the 2D. Yeah. You can see it easier, but I think the 3D bigger volume studies and the different temperatures and stuff is actually quite interesting. Yeah. And I think you will understand it better once you start printing some of those models. I think model making will help you to understand the three-dimensionality and the variance.
3D model.
Yeah, I think you need to start 3D printing some of those stuff. Well,
some of these?
Yeah, well, not the ones that are very loose, but the ones that they start getting different temperatures and you start getting this kind of voids, and you can even 3D print them in color and see these transitions. I think these catalogs actually are quite important in the way you progress your projects.
Yeah, that sounds interesting. I haven't thought of that.
Well, those ones you can 3D print, but the ones that they get more compact and they have some intersection logic.
No, we can find a way, because we can, for example, we can put this model in a Grasshopper, like what we did in workshop 2, and we can find a way to represent the bonds between them.
You can, yeah, you can, true.
So if we present the bonds, we can print them. Okay, yeah, yes. And generally about the feedback, we got, I think that everyone said that the computational part is pretty abstract, like, and Theo also insisted much that he is not sure about whether the particle system is helpful. And he was insisting on the generative aspect of, in the generative aspect of water, and how this could generate formations, I think.
Okay.
Correct me if I'm wrong, guys.
Yeah, he basically was talking about the snowflake, for example, generation, and how this would be more interesting than having just like having a particle system that just about phase change. But others like the phase changing. For example, Shajay was saying, don't just simulate just phase change, but also simulate what triggers and how and when triggers this phase change, which is interesting.
I think you're a bit in a, I mean, I agree. I think you're, but well, I agree and disagree. I think what you do is step-by-step process of developing a system, because you can't really focus on one thing at the moment. Phase changing is important. Now you're doing the whole range from solid to gas, which is normal. I think eventually you're gonna shrink the research towards solid to liquid only. I think the gas state is something that probably is not going to be as interesting because of architecture implications. If you want to have a system, somehow you need to be solid, so you can create some kind of, you know, stiffness and structure and something that can create architectural elements. And you may get into the water state because it's much more dynamic. I don't think you're going to go to the air. The air is, so once you start narrowing it, I think I agree with them that actually then not the phase changing necessarily, but the parameters that they affect the phase changing is actually going to be very important. Like the snowflake is a good one, but it's not a phase changing as such, but these parameters that they affect how the snow formulates different shapes and sizes and all that stuff. So that would be actually quite interesting to get more into the architectural let's say organization of those elements, and how you can move one step ahead and say, okay, I'm using the same logic to create architecture instead, not snow, obviously. I think that's why Theo kind of got pulled to the snowflake, because it's clear architecture, right? There's a three-dimensional aspect to it, where actually your simulations, they are right, they are abstract. They are the first step, though. I mean, we can, if you didn't do that, somebody's going to ask that. So I think it's a good thing. It's normal.
And Sergey, I think, was also more, he mentioned more the part of the how, instead of simulating the phase change, that we should insist more in the what triggers the phase change, also in the physical or the digital aspect. So that this is an important thing that we could develop more.
Well, effectively is what you were saying in the beginning about the bonds, and getting the part, go in the atom level and say what is happening in the, why phase change is happening. Obviously because of temperature change. We know what triggers it, but what we don't know is what is happening when they get triggered. What's happening in this process? I mean, you know, kind of, but simulating and let's say exploring that may actually give you some kind of control there that you don't know yet. But the triggering process, we know it. Well, kind of.
Yeah, I guess that, as you said, architecturally, maybe water seems more promising because it's more close to solid, to something solid.
Solid is the most promising.
Ice?
Yeah, well, ice, snow, if you consider it ice, but the solid state of water is actually what makes it more architectural. I think the dynamics of the water is actually also very interesting. The problem is that architecture is a frozen moment in time, usually. So that's where water starts getting weak. The liquid, actually, not water.
But the dynamics of phase change also, couldn't we say that it's somehow a dynamic thing, that we could use this?
The dynamics of phase change, actually, they could be instant, which is not like, you can turn from solid to liquid immediately, or from solid to gas. It's all about energy. If you put too much energy in it, it's going to happen. So there's no really dynamic. Well, there could be a dynamic state, but all I'm talking about dynamics in liquids, like, when you pour water down the drain, you start getting this kind of vortexes. You start getting this kind of ripple effects that they have to do with the viscosity of the water. They have to do with the materiality of it. So what you get is actually different depending on the liquid. But that's the dynamics of it, right? Or the flow of the water, or the water bending over because of the chemical bonds in the particles. All that stuff is properties that they give some dynamic feedback in our design, which are important. In the air, I think we lose that quite a lot. In the solid, it's a more fixed state. I think you're playing somewhere there, solid and liquid. If that makes sense.
I felt like that the evaporation is very, very interesting process, because it's kind of, you have this disappearance, like this notion of disappearance.
Yeah, well, true,
but it's not disappearance. Also, it goes somewhere. It is something, but you can't really see that.
Well, it's a little bit magician world.
Yeah,
you can have it in your mind, but I think you need some more concrete basis on architectural exploration, except if you want to go too abstract. But I think you need to play a little bit more on the safe side. It's already quite abstract as a material. It's difficult to handle. So I would say evaporation could be part of the system, but cannot be the main focus. I would think it more like you start from a very solid state, like ice scenario, and then you manage to generate out of it some kind of architectural element, which could happen through a liquid state, it could happen through a gas state, and evaporation there could actually be part of it. Like almost, how do you do an igloo in North Pole, but without, the traditional brick logic? Can you do it differently? What's the reason to do it differently? I don't know, but it's a design thing.
Mustafa also talked about patterning strategy.
What? Patterning?
Patterning, yeah. If you can share, Daphne, again, the latest simulations, the latest ones, they made like a patterning, how do you say, some patterns. Yeah. So he was talking about like two strategies in our project. The first would be the patterning strategy, and then we move on to the tectonic strategy. Yeah. And that we should look into this patterning and like study how to localize these patterns, how to create different patterns through localizing different temperatures in the for example. Yeah. So like in the 2D grid, it's easy to do that. In 3D, I'm not sure how this will have an apparent pattern, because we did the 3D. Mm-hmm. Although it was a small grid, but we did try in the 3D, and the thing is, it doesn't show as much as pattern as it showed in a 2D.
Yeah, but first of all, you did a very small sample, at least the one we see here. I think in 3D, I mean, you're right, it's harder to evaluate, but I think you can evaluate through sections. sectional cuts, which actually give you this kind of patterning that you want to read. Of course, an object that it's very hard to understand it, especially if it has voids and stuff, but that's where a section comes and helps. So I would encourage you, not yet, but soon, start 3D printing some of those things. Just understand what does it mean. And I think pattern making, I think this is the natural thing I think we've discussed, and I think that's what Mustafa says as well, is like, how do you control different scenarios within the same setup and actually start generating some pattern, which actually could be useful. Again, I think it's going to come from the solid aspect of things.
Solid only or liquid also?
I think it's solid. Well, I think wherever you have a hole, it's a liquid or a gas state. Wherever you have a more, let's say, no hole, let's say, a solid, that's more a solid state. I think that's what intuition, let's say, guides you to.
Yeah, this example is with an ice population.
Yeah.
You introduce more than 100, like, 130 Celsius area.
Yeah. But let's say if that was a three-dimensional grid, which is not, right, you would get a big chunk, which you couldn't evaluate in a 3D model like that. It would be like a, but what you could do is you can have a cutting plane and show what is happening in the depth of it. And then you can actually see this kind of cuts and how they start organizing space within this volume of ice. And that's kind of, a starting point.
Yeah.
It's almost like thinking about soap bubbles.
Yeah.
If you see all the soap bubbles, it's like, what the hell is this mess? If you start cutting them, you'll see that there is some organization within them. Well, this is why architects are dealing with these things. An engineer would say it's kind of a mass, but once you start using architectural techniques, you can start actually understanding those spaces better and those items. I think it's good though. But try to focus, try to think, how would you make a model out of it? I mean, I think you won't have the answer immediately, but try to be creative of how do you materialize that. I mean, I think it's something you need to start thinking without losing the abstract nature of your research, but start thinking how you can actually materialize. It's going to help you to bring some logic.
Yeah, true. It will be important. It will be nice to see that.
I mean, even if, I mean, we had that when we were doing our project as well, because we were effectively, particles in space. So how do you do a model out of it? Like any model we do, it wouldn't be working. But let's say we were thinking about what if we do these particles in water? Because in water, you can actually get that kind of stuff. Not that we did it, because actually there are complexities there. Actually, we did some of them, but we were mixing different liquids and stuff to see how actually in zero gravity, how things work. And we did experiments that in the first, let's say, reading of, it didn't make sense with the project somehow, but just in an attempt of simulating this kind of scenario actually helped us to progress. So you don't need necessarily to think, okay, we are talking ice and melt the ice and that's it. It's not only that. I think you can try to approximate in different, liquids or, I don't know, balloons. I don't know. This try to approximate what is happening in this kind of scenarios. How do you create separation? How you create cohesion? How do you maintain the volume of something, but at the same time, inside it, you get big pockets of empty space? I think you need to think creatively on how to actually make a model out of it. 3D
Mm.
printing is an easy way, but it's not performative. You want something that actually reacts.
Yep. So
what will happen, for instance, if you make a big ice cube, you put it in the freezer, but then in the middle of it, you have something that generates heat? What is going to happen? Like, there will be a core which doesn't get frozen, but the rest will start get frozen, no? I don't know what's going to happen. I mean, you're going to destroy all your freezers if you start doing that stuff, but you know, it's these things that I don't know. I think there could be crazy stuff generated by these processes. Like, how do you get the ice spike in the? It's because it is ice, but at the same time it was melting before. But how it's the process of how this appears and gets created is actually interesting, because it's a phase change, but it's a balanced phase change. So it's actually worth having a look.
Yeah, it's like a back and forth phase change from solid to liquid, liquid to solid.
Yeah, exactly. It's this back and forth actually generates a specific form.
Okay, yeah, I understand. All these are very interesting. I'm just wondering somehow whether this is too naive to think that we can control, because if we base our thinking in such a system, this demands a huge amount of energy. This demands, a huge amount of energy. So is it too?
But why you say so?
Because you have to heat something a lot, or you have to freeze something.
Yes, but if I tell you that you go to North Pole, that gets, I don't know, -40, right? So you get the cold by default. And then you kind of capture the energy from the sun and locate it in areas where actually you generate heat. But you don't change anything. You don't input any kind of energy. It's the physical conditions there. And then in a micro scale or in a mega scale, you start creating this kind of setups. I mean, it doesn't necessarily require a lot of energy. I know it's a bit of a naive approach, what I'm saying, but
I'm just discussing, like, just as an idea.
On the other hand, this is one way, right? But that doesn't necessitate that your project will be actually made through these processes. It could be designed by these processes. And that's why you're doing the simulations, right? It could be it's a designer tool. Instead of using Rhino to produce a 3-dimensional shape that is so crazy, you actually computationally, you simulate it and you get this 3D geometry, which then becomes your building. The main question is how this computational logic actually creates architectural functionality. How, let's say, ice could be a structural element. Is it a block of ice, the most architectural element you can get? Or there's a case where you can optimize the ice structure to work as a structure, but being lighter or being
grasshopper.
Yeah, one of the characteristics of ice is being less dense than liquid, for example, because it expands and then it's.
Yeah. So you don't necessarily need to see that as, we are building on ice with extreme energy requirements. It's the design tool. So don't get panicky about it. Like, everybody in the world is building with bricks, and we need to build with ice. No, it's not necessarily like this.
Who knows? Maybe it's the future.
Well, debatable.
Who wants to live in the Antarctic? I don't know.
Exactly.
Who wants to live there?
No, but effectively, if you want to be, let's say, realistic, and if you want to be, well, an architect, this is always to create new designs, right? Something that you haven't seen before. This is what the blunt architectural approach here is. Or create this kind of complex systems because they resolve systems that you cannot resolve by drawing lines by yourself. That's what computation is, effectively. It's how you go beyond, let's say, the human thinking. You make a machine think for you. So in that kind of that's more or less where that's kind of what we are doing here, trying to find setups, produce design through processes that the computer is doing, not us. We mostly fail because the architect side of things actually conquers our thinking, but not always. Make sense?
Yep. If we could find a way to prevent ice from melting, it could be much better.
Well, think about it. I don't think you can actually do it.
Yeah, we can't.
But what you can do, well, no, not really. But let's say melting ice. Well, can you, let's say, have an ice structure which then you rigidify with some other material, like, I don't know, FRP or whatever, some kind of fiber polymer or something. And then once the ice melts, then all the very heavy part of the scaffolding is gone, and then you're left with this very thin cell that actually can stay by itself. You know what I mean? Like almost like a wax cast.
Yeah, I get.
I don't know. I don't think it makes necessarily sense, but you can always start thinking about processes that, as you say, how do I make the ice stay without being cold? I don't know. Maybe you don't, but maybe you utilize the ice for a different reason. Not for staying, but for formulating something.
Yep.
Okay?
Yep.
Yeah.
Well, but good progress for a week. Thing is,
Thank you.
Nice stuff.
Yeah, we are our team.
Air.
Yeah.
We are getting from complex to even more complex. Like from water that is abstract to something like good luck. Air.